Everybody, welcome back to chemistry. And so we're continuing on through chapter 7. So now we're getting into some problem solving using some things called simple gas laws. And so I want to sort of point out first where you can find more information about these simple gas laws. And so one of the simple gas laws we're going to go over is Boyle's law, which is found in section 7.2 of your book. Also, we're going to go over Charles's law, which is found in section 7.3 of your book. And then finally, there's another law called Aminoton's law that is not covered in your text, but it can be found in the OpenStax textbook on the internet in section 9.2, and I have a link for that there that you're welcome to look at. Okay, so we're going to be looking at simple gas laws that when we're given certain properties of gases, we can calculate the value of the other properties. So I need to sort of mention here, what are the four major properties that you can measure about in a gas? And so you can sort of see there, they are volume, temperature, pressure, and moles. So let me just talk a little bit about that on the light board. So let's say you have a flask. So here's my flask. And let's say it is tightly stoppered here. And so inside the flask, we have air. And so air is a mixture of gases. And so we can, now we can just consider it a gas. So we have air molecules in here. And so I'm drawing little dots here to describe air molecules. But this is not really representative of what's going on because air molecules are not moving. They are moving, and they're moving very fast, even at room temperature. The average speed of an air molecule at room temperature is 1,200 miles per hour, so they're moving very, very fast. So to give us some kind of sense that these air molecules are moving around, I'm going to just draw arrows like this in just different directions. And this is just a reminder that the air molecules are moving around very fast and they're going all kinds of different directions. And so, as you might guess, some of these air molecules will collide with each other every once in a while. Now, here's a question for you. These air molecules are moving at 1,200 miles per hour. That means right now I'm being struck by air molecules moving at that speed. Why am I not crushed into smithereens? And the reason is because despite the fact that these air molecules are moving so fast, they have tiny little mass. In fact, very, very, very little mass. And so when they strike me, because their masses of these air molecules are so low, they don't impart a lot of kinetic energy into me. And so I don't receive much energy when these air molecules strike me, so I'm fine. But still, a reminder that these air molecules are traveling very fast. Okay. Now, let's talk about how you measure the properties of a gas here. So you can figure out the volume of a gas pretty easily. And so the way you would do that is you would just note the volume of the container it is in. And so that should tell you the volume of the gas. You can also figure out the temperature of the gas pretty easily by sticking in a thermometer. Okay, how about pressure of the gas? Well, let me kind of talk a little bit more about what pressure is. And so this gas is exhibiting pressure against the sides of this flask. So let's think about how that is happening. So what will happen is you'll have a gas molecule and it'll strike the side of the flask. And so it won't be just one, there'll be a lot striking the sides of the flask. And so they're going to be striking the sides of the flask with a certain force. Now the force is going to be very, very small for each gas molecule, but if you consider all the gas molecules striking at once, that force will add up. And so what pressure is a measure of the force that these gas molecules collide over a certain area. So I'm just going to mark here, say from here to here, A here for an area of the flask. So let's think about how we could increase the pressure of air molecules on the flask. Well, there are two ways you can do it. One, you can put in more air molecules. So if you have more air molecules, they'll be striking, more will be striking a particular surface, and so that will increase the pressure. But there's another way you can increase the pressure. Another way you can increase the pressure is by increasing the temperature of the gas. If you're increasing the temperature of the gas, then you have molecules that are traveling much faster. So I'm going to try to draw longer arrows here, indicating here that maybe I've increased the temperature and that causes the molecules to move faster. So if so, they're going to strike the surface of the flask harder, and when they do, that should increase the pressure. So what we're going to do now is look at a couple of gas laws. And so let's start with the first one. We're first going to talk about Boyle's law. So what Boyle's law is about is studying the relationship between the pressure and the volume of a gas, keeping the other properties of that gas constant. So this is where you're looking at pressure versus volume of a gas, holding temperature and the number of moles of gas constant. So let's talk about what the qualitative relationship between pressure and volume of a gas is, and then the quantitative relationship. So let's say that we have a gas and it's in some kind of flexible container, meaning the volume can change. Now let's say that what we did is we reduced the volume of the gas in that container. Can you imagine what would happen to the pressure of that gas? So if you have reduced the volume of the container, you reduce the area in which the air molecules are striking or the gas molecules are striking, and so you're going to increase the pressure. So we know the qualitative relationship now between volume and pressure of a gas. That when you reduce the volume, you increase the pressure. Likewise, if you were to increase the volume, you would decrease the pressure of the gas. And so when you have one variable going up and the other variable going down, going the opposite direction, then what we say is that those two variables are inverse of one another. So pressure and volume of gas are inverse of one another. So we can sort of describe this with a very simple equation, which I have there. You see on the screen, there's P for pressure, and then there's that weird squiggle. That weird squiggle is a symbol for proportionality. And then you can see that pressure is not proportional to volume. It is proportional to the inverse of volume. And so that expresses the fact that when you increase pressure, then volume would decrease. Now, if you wanted to, you could take this qualitative relationship between pressure and volume and make it a quantitative one. In other words, we can take this relationship and then maybe adjust it slightly so we can actually throw some numbers into it and get values. And so what would we do? So if you want to turn it into a quantitative relationship, what we do is we have to put in a K, a constant value. And then you can put it on that side of the equation, which is fine. And then once we have a quantitative relationship, it's no longer a proportionality. It is an equality. So I've replaced the proportionality constant with an equal sign. And so that will be a good equation to describe the relationship between pressure and volume of a gas. Now we can rearrange the equation a little bit. So what we can do is we can move V from the right side of the equation to the left side of the equation. When you do that, it goes into the numerator. And so what you can see is that whenever you have a gas, whatever its pressure and its volume are, if you multiply them together, it will be a constant value. So that's kind of remarkable. You can change the volume of the gas, but its new pressure, when you multiply it by that new volume, will be equal to the same constant value that it was before. Let's kind of look at some of the more quantitative aspects of the relationship between pressure and volume of a gas. So let's say you have a gas, and let's say you reduce its volume to be 1/2 of the original volume. Its pressure will go up 2 times. If you reduce the volume of the gas to be 1/3 of its original volume, its pressure will go up 3 times. If you reduce the volume of gas to be 1/10 of its original volume, its pressure will go up 10 times. So that is a nice quantitative relationship between pressure and volume. So as an example, let's say that you had a gas and it's originally at 2 liters of volume and its pressure is 2 atmospheres. Okay? Now let's say you reduce the volume of the gas to be 1/10 of that. You're going from 2 liters to 200 milliliters. You've reduced it by 1/10, so it's a very small volume. What would happen to the pressure of the gas? It would go up 10 times. It would go from 2 atmospheres to 20 atmospheres. And so you can sort of see that kind of reflected there in that top graph. And if you look carefully, what you'll see is that we have one condition where the gas is at 2 liters and say, for example, at 0.6 atmospheres. If you double the volume of the gas to 4 liters, you have the pressure to 0.3 atmospheres. So this relationship is always true for a gas. So one way we plotted there on the top is we have volume there on the x-axis and pressure on the y-axis. And you can sort of see the relationship between pressure and volume of a gas is not a straight line. It is a curve. Now, if you wanted to, you can do something which is called linearization. If you have a curved line, a hyperbola like that, you can linearize the data by taking the v on the x-axis and then changing it to 1 over v. And when you do that and you plot it against p on the y-axis, it's the same data, but just the way the numbers are, now you have those points in a line. Okay, so here is sort of an explanation as to why is it that when you reduce the volume of a gas, the pressure goes up. And this may be already common sense. So here on the left side of the diagram there, on the lower left, I have a gas that's contained in a volume of 1 liter. And it looks like the pressure of that gas is being measured to be 1 atmosphere. And so that gas could be air, or it could be some individual gas like nitrogen or oxygen or something like that. Now, as I was saying before, if you reduce the volume by half, then you're going from 1 liter to 0.5 liter, you will double the pressure. You'll go from 1 atmosphere to 2 atmospheres. So why does the pressure increase? Well, it's pretty simple. When we reduce the volume, we still have the same number of molecules in there, right? The number of moles of the gas remain constant. So we still have the same number of molecules, but now they're striking over a reduced area. If that is the case, the same number of molecules forced to strike over a reduced area, that's going to increase the pressure. And so that's why the pressure goes up. Okay, so again, here I'm just sort of expressing the key qualitative relationship here with a gas, that if volume decreases, then the pressure will increase. And this is called Boyle's law. So on a test, they may ask you questions about that, but what they'll more likely do is they're going to ask you some problem where you have to quantify the values of a gas, taking sort of a gas at a known pressure and a known volume, and you're changing it to, say, a new volume, and you have to figure out what the pressure is. And so that's what we're kind of doing here. So let me show you how to do that. So we're going to do that with this problem. So sort of the key formula that you need to know in solving this problem, this is one that I haven't shown you on the slide, is that with Boyle's law, one equation you can use to help you solve problems is that P1 times V1 is equal to P2 times V2. So P is pressure, V is volume for a gas. 1 are original conditions, 2 are the new conditions. And so let's go to try this problem. It says a sample of oxygen occupies 10 liters under a pressure of 790 torr. At what pressure will it occupy if you're changing the volume to 13.4 liters if the temperature does not change? Okay, so what we're going to do is we're going to try to find what this new pressure of the gas is when it changes into a new volume, holding the number of moles and the temperature of the gas constant. So the way we approach this is probably to first assign variables. So let me go ahead and do that. So we have P1, and P1 is going to be 790 torr, which is a pressure. And then we have V1, which is 10.0 liters. and we're trying to find a new pressure, which is P2, and then we're given a new volume, which is 13.4 liters. Now let's just step back and take a look at this information and see if we can sort of predict, what do you think in the new condition, which is 2, will the pressure be greater than it was, or will it be less than what it was? So we started out with a pressure of 790 torr and a volume of 10 liters. Now we're going to increase the volume from 10 liters to 13.4 liters. So that would predict that we must decrease the pressure. So one thing we can look out for is when we're figuring out an answer, we can make sure that the pressure is less in our new conditions than it was in the original conditions. Okay, so basically you have to take this equation and solve for P2. So we have P2 here, and so let's talk a little bit about how you might do that. So here we're trying to solve for P2 here, and so we have to move V2 to the other side of the equation. So right now it's in the numerator, and so when you put it onto the other side of the equal sign, it will go into the denominator. So let me rewrite this. It's going to, P2 is going to equal to P1 V1 over V2. And now at this point, we can maybe plug in numbers. But before I do, let me ask myself this question. Do I have to take any of these numbers here, which are in particular units, and convert them to other units? Now, if it was a temperature, the answer would be yes. If you have a Celsius temperature, you must convert that to Kelvin. On the other hand, with Boyle's law, if you have pressures and volumes, you can use the units as is. You do not have to convert these units to something else. So for example, if you had a problem in milliliters, you would not have to convert it to liters if you can accept that your answer in milliliters will be the same as the original value in milliliters, for example. Here with pressure, torr is fine. You have to, though, you'll receive a value for the answer in torr, which was, the units used for the original pressure. So let's go ahead and throw in some numbers. So we have 790 torr, and multiply by the volume of 10.0 liters. Oop. Don't know what happened there in my brain. 10.0 liters, and then you divide that by 13.4 liters. And so this will tell you the new pressure that this gas has at its new volume of 13.4 liters. And so if you work that out, I think the answer you get is 590 torr, which is less than the original pressure, so that is what we expected. Okay, so let us move on.